All right, so let's compare this vector cross product to the scalar dot product. So, okay, what's this? Vector or scalar? Obviously, it's work with no vector sign, so that's scalar. Here, it's vector. Agree? Vector. All right. Let me just draw it. Hold on. So, okay, so this is a scalar. This is a vector. All right. Where, for what angle will this be a maximum? So think of work, right? If you want a lot of work, the force is in the same direction as displacement, right? So 0, right? 0 degrees. Now, where is this going to be a maximum? Remember, this is cosine. This is sine. So we're going to have the maximum torque. The maximum torque. Well, what's maximum sine? 90. Right? So when these guys are perpendicular, you have the largest torque. Well, we already know that, right? When you open the door, you know, let's say the R is this way, you want the force perpendicular to that. So that makes sense. Okay, for what angle is this 0? Well, just think, right? If you have something moving along a tabletop, does gravity make it go faster or slower? No, that doesn't affect it at all, right? So in other words, the work done by gravity as something is going on a tabletop is 0. So theta for this is 90. All right, now torque. This is sine. What angle has a sine of 0? 0, right? And that's like, remember, opening the door. So this is a door. If I push this way, waste of time, right? Okay, so that's 0. And then the trig function, again, this is cosine, and this is sine. So you see, I mean, they're very, very different, right? So, I mean, you can't get them confused, or you're going to be in big trouble. But I think that the easiest way to think of it is, you know, I like this personally. You know that this one here, if something's moving this way and the force is this way, it's not going to do anything, right? And so the work is 0 if you have 90 degrees. I don't know. But this, it's opposite, right? Just opposite. Or this one. This makes good sense too, right? The maximum work is when the force is in the same direction as the displacement, you know? So this should be very clear, and this is just opposite. So, however you want to look at it, you know? All right. Okay, now, I still haven't told you how to evaluate it. Okay, all right, so I want to get the magnitude and the direction. I have two vectors, right? Remember, torque is R cross F. Two vectors. So this would be like my R vector. This would be my F vector. So we've got to learn how to do this to get the magnitude and the direction of torque. So you remember at the beginning of the semester you had to pass that math exam? And one of the questions on the math exam was evaluating a determinant. Why did I ask you that? Because that's how you evaluate a vector cross product. So this is just one way. I mean, there's other ways of doing it, but this is one way. So I'm going to show you how to evaluate this determinant in case you've forgotten. Okay, so here's how you do it. So I'm going to do it this way. I'm going to go along this way. You don't have to, but that's what I'm going to do. Okay, so how you do it is this. So you write down the I. All right, and then what you do is you cross this out in your head. You cross it out in your head, then you have just this left. And this is a 2 by 2 determinant, and hopefully remember how to do that. How do you evaluate a 2 by 2? It's this product minus that product. So it's I times this minus that. So it's AY BZ minus AZ BY. Okay? Then, so we're done with this one. Now I go here. So it's a 3 by 3, right? So it goes plus, minus, plus. If it were 4 by 4, plus, minus, plus, minus. So it's minus J, and then in your head, you're going to cross out this because it contains a J. You're going to cross out this because it contains a J. Now you have this and this left over, right? You have a 2 by 2 again. So it's just that product minus that product, just 2 by 2 again. So AXBZ, so AXBZ minus AZBX, right? Okay, now plus, minus, plus, so we have plus K hat, all right? So what you do, so you cross this out because it contains a K, you cross it out because it contains a K. Now you have this 2 by 2. So same as always, that product minus that product. So AXBY minus AYBX. There you go. All right, so that's how you do it. Now there's other ways of doing it. I like this way because, you know, if you know this method, you can use it for a 2 by 2, 3 by 3, 4 by 4, whatever. You know, it doesn't matter. I've seen some people, they have this funny method. I call it funny. They write something over here, then they do some weird things. I don't know. But it only works for a 3 by 3, so I don't think it's any good. But well, if you want to do it, go ahead. You know. Okay. So if we were meeting face to face, I would have the first half of the class do A cross B. Now let's have the second half of the class do B cross A. So since we're not meeting in face-to-face, and we all want to get practice, right? So I'd like you to pause your video, calculate A cross B, and then calculate B cross A. So honestly, pause your video, use that formula or whatever weird way you would like, just kidding, and calculate these two, please. All right, you can unpause or whatever. All right, so this is what you should get. You get A cross B, you get 5I plus J minus 2K. When you do B cross A, you get minus 5I minus J plus 2K. So what do you notice? You notice that A cross B equals minus B cross A. So the vector cross product is not commutative with respect to multiplication, all right? You know, with math, right, 2 times 3 equals 3 times 2, right? Or A times B equals B times A, but not so for the vector cross product. Okay, so you got to watch it. So in other words, so when we write that formula, torque equals R cross F, we mean it, all right? We do not write torque equals F cross R, because if we do that, we're going to get the opposite direction. So this is wrong. Okay? So the order is important. R cross F. Okay? So you got to just be aware of that, you know? You got to be aware of that. And again, we're going to use this to calculate something called angular momentum later on in this chapter. And then in Physics 220, we're going to use it all the time, all right? So you're going to know it. All right. Now, remember how we had conventions for omega, right? We said if something's moving clockwise, we said the omega is negative. If something moves counterclockwise, omega is positive, right? So we're going to use the same conventions with torque, which is kind of nice, right? So counterclockwise, torque is positive. Clockwise, torque is negative. You have to know that. When we start doing torque problems, you have to insert the signs. And if you don't, you get the whole problem wrong. Okay? So you got to be careful. All right. So, you know, equilibrium, right? We've talked about that a lot, equilibrium. But in the past, we just said that the equilibrium was the sum of the forces equals 0. Well, now we have the ability to rotate, you know? So it's not just the sum of the forces equals 0, it's also the sum of the torques equals 0. So there you go. Equilibrium, sum of the forces is 0, sum of the torques is 0. So we have two things to worry about, okay? Remember that? Remember that problem we did? And I tried to explain the easy way to do it, but then I also said you can do it with torques. So let's do it with torques. So the meter stick is obviously not rotating, so the sum of the torques equals 0, right? So the sum of the torques equals 0, right? Okay, so let's just use this definition. Torque equals force times lever arm. So this one, okay, so this is the force. I'm just going to say, right, this is the force. This is the lever arm. Now what's the direction here? Counterclockwise, right? So this would be, it's counterclockwise, so it's a plus. I'm going to put a plus just to emphasize it. So it's plus 1 kilogram times 9.8 meters per second squared. So that's the force. Lever arm perpendicular distance is 0.25 meters. 0.25 meters. Okay. Now here, we said that the mass of the meter stick can be considered to be at the center mass of the meter stick, right? So we wanted to determine what that mass was. So the force here would be the m, mass of the meter stick, times g. But wait a second, it's going clockwise, so we have to give it a minus sign. So minus m times 9.8 meters per second squared. And what's the lever arm? So here's the force line. Here's the lever arm, 0.25 meters. 0.25 meters. And that has to be 0. That looks stupid. All right? So obviously, look at it. What does m have to be? M has to be 1 kilogram, right? So there you go. Okay, so that's another way to do it. You didn't have to do it with torques, but it doesn't hurt. All right, let's do a torque problem. A typical, I don't know typical, but relatively easy torque problem. But you're going to see there's a lot more to it than just a force problem. Yeah, I already said that. Okay, oh my gosh. A uniform beam of mass 1.96 newtons, so of weight 196 newtons, and of length 1 meter is attached to a hinge on the outside wall of a restaurant. A cord is attached at the center of the beam and is attached to the wall, making a 30-degree angle. The cord keeps the beam perpendicular to the wall. Got it. If the breaking tension of the cord is 620 newtons, how large can the mass of the sign be without breaking the cord? This is kind of a reasonable question, right? I mean, if you're going to put a sign on the beam, you better not break this and have somebody walk underneath and get killed, right? Okay, so this is a good torque problem, right? Because if this breaks, this beam is going to rotate, you know? So there's torques because there's rotation. Okay, first question. So in other words, we want this thing to be in equilibrium, right? We don't want any movement at all, you know? So what are the conditions for equilibrium? I already told you, right? That. Okay, great. Okay, now let's get back. Okay, first question, what's the object? Is it the sign? Is it the beam? Is it the rope? I mean, what's the object? What are the forces acting on? What are the torques acting on? What's the object? It's the beam, right? The beam. So the beam is the object. Okay. What are the forces that act on the beam? Well, you know, it's gravity, right? There's gravity. Yeah. So I'm going to call it MBG. You got to put subscripts, right? Because we have the mass of the sign, we're going to have the mass of the beam. So there's m, so there's the weight of the sign, right? Gravity's pulling down on the sign. What else? Well, there's weight. I mean, there's the weight of the sign. Now, wait a second. You should say, wait. There's tension. Well, okay. So the tension here equals the weight of the sign, right? And what we're interested in is the weight of the sign. So we're not going to say tension. We're just going to say the weight of the sign because it's the same thing, okay? All right, so there's that. What else? Well, all right, tension of the rope, agree? Let's see. Okay, and you know we want to say it's 620 newtons, right? Because we're trying to find the maximum mass of the sign. All right. So we'll say there's the force of the rope, which is 620 newtons. Okay. What else? Well, isn't there like a normal force? Right? If this were tissue paper, this beam would go that way, right? So there's a normal force. So I'll say the normal force of the wall. Okay, what else? Well, think about it. This is kind of acting like a, this is pulling down on it, right? This is pulling down. So, I mean, so it kind of wants to go like this, right? Right? The sign is pulling down. So it's kind of like, it wants to go like that, right? So there has to be some kind of a vertical force there as well, all right? Don't worry about it because we can get rid of it. So there has to be some kind of a vertical force as well. Whoa! Okay, now, so how many forces? 1, 2, 3, 4, 5. Okay, that's not the worst part. The worst part is, remember, this is an extended object. It's a beam. It's not a point. With a force diagram, you just draw all the forces on the point, right? This is an extended object, so you have to draw the forces where they're actually occurring. So, the weight of the beam, where do you draw that? Think back. Center mass, right? So this is the center mass, so you draw it right there. Here's the weight of the sign. Here's the tension of the rope. Here's the normal force. There's some vertical thing. So you got to draw the force diagram, but you got to draw it carefully, So there's the force diagram. Weight of the beam, weight of the sign, the 620 newtons for the rope, normal from the wall, and this other thing that we're going to get rid of. All right? Okay, there you go. All right, now, in my opinion, the easiest way to do this is you usually want to first write the torque equation. Sometimes that's all you need. Sometimes you have to write the force equations too, but sometimes you just get away with it just writing the torque equation. So I always write the torque equation first. Now, the beauty of it, remember, what is the axis of rotation? Who chooses the axis of rotation? Actually, it doesn't matter. You can choose any axis of rotation you want to. It's completely arbitrary. But there's a smart way and a not so smart way. The smart way is to choose the axis of rotation so you get rid of as many forces as you can get, or let's say you get rid of as many torques as you can get, so you have less work to do. So where can I put an axis of rotation? It doesn't matter, honestly. You can put it here, 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 anywhere actually, but I want to put it somewhere so I have no torque. Sorry, not no torque, but I'm going to get rid of some of the torques. In other words, I want to look for a place where I have 0 lever arms. All right? Lever arm equals 0. That's better, right? So I want to have some lever arms that equal 0 so I can get rid of those torques. So where's a good place? Think about it. I hope you agree. If I put the axis of rotation here, there's no lever arm for this guy, there's no lever arm for this guy, so I don't have to worry about him. Awesome. All right? So there's my rotation axis right there. So I killed off these 2 torques. Isn't that great? Awesome, right? Right. And it's easy to figure out the lever arm for this guy, easy to figure out the lever arm for this guy. Now this guy's a little bit more difficult. So here's your force line. And the lever arm is the perpendicular distance from the force line to the axis. So there it is, right? Perpendicular distance. There's the force line, perpendicular distance, right? Distance in meters. Okay, now it's not so bad. So, a picture's worth 1,000 words, right? You got to get this picture right in order to solve the problem. All right. Awesome. Ready? Here we go. Now, we don't want any movement, right? We don't want any, so we want the sum of the torques to be 0. So the sum of the torques, we want to be 0. All right? And it doesn't matter the order, of course, so let's just do it. Okay, let's do this one first. So this is the axis. Just think of this force, nothing else. Forget about the rope, forget about this. Just think of this. If this is the only force acting on this beam, with this as the axis of rotation, it's going to be clockwise or counterclockwise? Well, obviously, you know, it's going to be clockwise, right? So what does that mean? You got to insert a minus sign. And you have to remember that. I mean, it's just how it is, you know. So minus sign. Okay, so what's the torque? Well, the force is m sine g. What's the lever arm? Here's the force line. Perpendicular distance from the force line to the axis is this. So just 1 meter. Awesome. 1 meter. All right? Then let's do this one. All right, so the force is, okay, again, ignore that, ignore that. All we have is the weight of the beam. Is it going to be clockwise or counterclockwise? Well, it's going to be clockwise. So we've got to put that minus sign. So minus m beam g. What's the lever arm? So here's the force line. Perpendicular distance from that to the axis is this, 1/2 meter. 1/2 meter. All right, now we're left to the rope. Okay, so ignore that, ignore that. This is the axis. You're pulling this way. What's it going to do to the beam? Counterclockwise or clockwise? Counterclockwise, so put a plus. All right, so it's the force. I'll just say FR, lazy. FR. Now, what's the lever arm? Remember, it's a distance, right? So what's this D? Well, this is a 1/2 meter. This is opposite, so it's sine, right? So it's 0.5 meter sine 30. 0.5 meters times sine of 30. Okay? And that has to equal 0. All right, so we're going to solve for MS. So let's put this on this side. So we'll have MSG times 1 meter equals all that other junk. Let's see, minus MBG 1/2 meter plus FR 0.5 meters sine of 30. Okay, and then we're going to divide by the G. We're going to divide by the 1 meter. And I promise you, you do that, you get 5.82 kilograms. Okay, so there you go. So let's review. You know, you got to first figure out the forces and where they are applied. You got to draw the force diagram correctly, where the force is applied. You got to choose the rotation axis. I mean, this seems to be the logical one, but again, you can choose anything. Anything you want will work. But you want to choose it so you minimize the number of torques. So you do that, and then you just figure out the torques. But I know a lot of students forget about the signs. You can't forget about the signs, right? If it's a counterclockwise torque, it's a plus. Clockwise torque is a minus. And just look at them one at a time, you know. I've also seen students where they think they're trying to calculate this lever arm, and they say like 620 newtons sine of 30. That's insane, right? It's a lever, it's a distance, right? It's a distance. So, I mean, it's 0.5 meters sine 30 or something, okay? Forget about that. In order to calculate that, it's a distance. Then you just do it. Now, this one was nice because we just had to do the torque equation. We didn't have to do any force equations. Now, sometimes, like the next one, it's not so nice. So you have to use, you know, I always start with torque, so I think that's wise. Start with torque, but then you might have to do some force equations as well. So let's quit.